Torch complex. Description: explain in detail the torch complex function in P-torch is used to create complex tensors from real tensors. Complex tensors are represented as two-element tensors, where the first element is the real part and the second element is the imaginary part. Inputs. Input 1. Explain in detail real. A real tensor representing the real part of the complex tensor. Input 2. Explain in detail IMAG. A real tensor representing the imaginary part of the complex tensor. Outputs. Output 1. Explain in detail a complex tensor containing the real and imaginary parts provided as input. Steps. Step 1. Explain in detail the torch complex function takes two real tensors, real and IMAG, as input. Step 2. Explain in detail it constructs a new complex tensor where each element is a tuple containing the corresponding real and imaginary values from the input tensors. Challenges and fixes. Challenge 1. Explain in detail input tensors should have the same shape or be broadcastable. Sample use case that resulted in challenge 1: trying to create a complex tensor from real tensors with different shapes will result in an error. Fixes to challenge 1: ensure that the input tensors have compatible shapes for broadcasting. Challenge 2: explain in detail the input tensors should be of floating point data type. Sample use case that resulted in challenge 2: attempting to create a complex tensor from integer tensors will result in an error. Fixes to challenge 2: convert the input tensors to floating point data types before using torch complex. Torch real. Description: torch real is a P-torch function used to extract the real component of a complex tensor. Complex tensors are represented as tensors with complex numbers, where each element has a real and an imaginary part. Inputs. Input 1: a complex tensor. Input 2: none. Outputs. Output 1: a tensor containing the real components of the input complex tensor. Output 2: none. Steps. Step 1: the function iterates through each element of the input complex tensor. Step 2: for each element, it extracts the real part and stores it in a new tensor. Challenges and fixes. Challenge 1: input tensor is not a complex tensor. Sample use case that resulted in challenge 1: passing a regular float tensor as the input. Fixes to challenge 1: ensure that the input tensor is a complex tensor. Torch complex 64 torch complex 128. Challenge 2: none. Sample use case that resulted in challenge 2: none. Fixes to challenge 2: none. Torch IMAG. Description: Torch IMAG is a Python library designed for image processing and manipulation using P-torch. It offers a wide range of functions for image loading, transformation, augmentation, and analysis, all leveraging the power of P-torch tensor operations and GPU acceleration. Inputs. Image data. Torch IMAG typically takes images as input. These images can be loaded from various sources like files, URLs, or memory buffers. The images are represented as P-torch tensors, allowing for efficient processing using P-torch tensor operations. Parameters. Torch IMAG functions often accept parameters that control the image processing operations. These parameters include things like image size, cropping regions, rotation angles, brightness adjustments, and more. Outputs. Processed images. Torch IMAG functions return processed images, also represented as P-torch tensors. These processed images may have undergone various transformations, such as resizing, cropping, color adjustments, or augmentation. Analysis results. Some Torch IMAG functions may return analysis results, such as feature maps, bounding boxes, or segmentation masks, depending on the specific image processing operation. Steps. Image loading. Torch IMAG functions typically start by loading images from specified sources. This can involve reading image files from disk, fetching images from URLs, or accessing images already loaded into memory. Tensor conversion. The loaded images are converted into p-torch tensors. This allows the image data to be efficiently processed using p-torch powerful tensor operations. Image processing. The core image processing takes place in this step. Torch IMAG provides a rich set of functions for various transformations and augmentations, including resizing, cropping, flipping, rotating, color adjustments, blurring, noise addition, and more. Output generation. After processing, Torch IMAG functions return the processed images as p-torch tensors or, depending on the function, additional analysis results. Challenges and fixes. Challenge 1. Handling different image formats. Torch IMAG needs to be able to work with various image formats: JPEG, PNG, etc. Sample use case that resulted in challenge 1: trying to load an image in a format not supported by the library. Fixes to challenge 1: use libraries like PillowPIL to handle image formats that Torch IMAG doesn't natively support. Challenge 2: memory management for large images. Processing large images can lead to memory constraints. Sample use case that resulted in challenge 2: attempting to process very high resolution images on devices with limited RAM. Fixes to challenge 2: use techniques like batch processing to divide large images into smaller chunks, process them individually, and combine the results. Consider using GPU acceleration to handle large image processing tasks more efficiently. Challenge 3: maintaining image quality during transformations. Some transformations, like resizing or cropping, can lead to image quality degradation. Sample use case that resulted in challenge 3: resizing an image to a smaller size while using a simple interpolation method, leading to blurring. Fixes to challenge 3: use higher quality interpolation methods, such as bicubic or Lancizos. For resizing, experiment with different interpolation techniques to find the optimal balance between speed and quality. Challenge 4: efficiently applying augmentations. Repeatedly applying augmentations can be time-consuming, especially during training. Sample use case that resulted in challenge 4: applying multiple augmentation steps to an image during each training iteration, slowing down the training process. Fixes to challenge 4: use p-torch data loaders to create a pipeline that efficiently applies augmentations to images in batches during training. Consider leveraging GPU acceleration to further speed up the augmentation process. Torchpolar. Description. Torchpolar is a function in p-torch that converts Cartesian coordinates to polar coordinates. It takes two tensors representing the x and y coordinates as inputs, and outputs two tensors representing the radius and angle in polar coordinates. The angle is returned in radians. Inputs: x, a tensor representing the x coordinates of the points, y, a tensor representing the y coordinates of the points. Outputs: r, a tensor representing the radius of the points in polar coordinates. Theta, a tensor representing the angle of the points in polar coordinates in radians. Steps. The function calculates the radius using the formula RSQRT(x2y2). The function calculates the angle using the formula theta arctanx. Challenges and fixes. Challenge 1: division by zero error when x is 0. Sample use case that resulted in challenge 1: converting points with x coordinate equal to 0 to polar coordinates. Fixes to challenge 1: The function handles the case when x is 0 by setting the angle to pi2 if y is positive and pi2 if y is negative. Challenge 2, handling negative angles. Sample use case that resulted in challenge 2, converting points in the second and third quadrants to polar coordinates. Fixes to challenge 2. The function adds 2 pi to the angle if it is negative to ensure that the angle is in the range 0. 2 pi. Torch angle. Description: torch angle refers to the angle at which a torch is held relative to the workpiece being welded. This angle directly impacts the quality and effectiveness of the weld. Inputs: torch angle, the angle between the torch and the workpiece. Welding process, the specific welding process being used, such as TIG, MIG, or stick welding, as each process has different optimal torch angles. Material being welded, the type of metal being welded, as different metals require different torch angles for optimal penetration and bead formation. Desired weld bead profile, the desired shape and size of the weld bead, which can be influenced by torch angle. Outputs: weld bead profile, the resulting shape and size of the weld bead, which is directly influenced by the torch angle. Penetration depth, the depth to which the weld penetrates into the base metal. Weld quality, the overall quality of the weld, including factors such as strength, uniformity, and appearance. Steps: setting the torch angle, the torch is adjusted to the desired angle relative to the workpiece. Starting the welding process, the welding process is initiated, and the torch is moved along the weld joint, maintaining a consistent angle throughout the welding process. The torch angle is carefully maintained to ensure a consistent weld bead and penetration depth. Inspecting the weld: once the weld is complete, it is inspected to ensure that the desired weld quality has been achieved. Challenges and fixes. Challenge 1: excessive penetration. If the torch angle is too steep, the weld may penetrate too deeply into the base metal, leading to weld defects such as burn-through or excessive undercut. Sample use case that resulted in challenge 1: a welder welding a thin sheet of metal with a steep torch angle, resulting in burn-through. Fixes to challenge 1: reduce the torch angle, lower the torch angle to reduce the heat input and prevent excessive penetration. Reduce welding current, decrease the welding current to reduce the heat input. Use a smaller diameter welding electrode. A smaller diameter electrode will reduce the heat input and penetration. Challenge 2: insufficient penetration. If the torch angle is too shallow, the weld may not penetrate deeply enough into the base metal, leading to a weak or incomplete weld. Sample use case that resulted in challenge 2: a welder welding a thick piece of metal with a shallow torch angle, resulting in insufficient penetration. Fixes to challenge 2: increase the torch angle, raise the torch angle to increase the heat input and penetration. Increase welding current, increase the welding current to increase the heat input and penetration. Use a larger diameter welding electrode. A larger diameter electrode will increase the heat input and penetration. Challenge 3: uneven weld bead. An inconsistent torch angle can lead to an uneven weld bead, which can affect the strength and appearance of the weld. Sample use case that resulted in challenge 3: a welder welding a long seam with inconsistent torch angle, resulting in an uneven weld bead. Fixes to challenge 3: use a jig or guide. Using a jig or guide can help to maintain a consistent torch angle throughout the weld. Practice proper technique. It is important to develop proper welding technique to ensure a consistent torch angle. Use a welding manipulator for complex welds. A welding manipulator can help to maintain a consistent torch angle.